Hello, everyone. I am Jerry Anunrojwong, a PhD student at Columbia Business School. Today, I would like to talk about my work on the robustness of second price auctions in prior independent mechanism design joined with Santiago, Balseiro, and Omar Besbes. So mechanism design is a way to systematically design the rules of the game, or a mechanism to achieve an objective. Here is to maximize revenue, while taking into account incentives. And the classical theory assumes that you know the environment perfectly and design the environment with that in mind. In particular, it assumes that a common prior is known. Often it also makes strong assumptions on agent behavior, like agents are Bayesian and plays a Bayes-Nash equilibrium. And this theory is very elegant, but it depends too intricately on details about the knowledge of the common prior and how bidders behave strategically. And so this raises two fundamental questions on what is an optimal detail-free mechanism and how much can we expect to perform without details relative to the best we could do. And this work is the first to give prescription for an arbitrary number of buyers across a wide spectrum of distribution classes that capture the dependency structure of agents from independent through arbitrary and the intermediate regimes. We now formulate the problem more formally. We want to sell one indivisible good to n buyers, and note here that the number of buyers is arbitrary. This is in contrast to quite a few of the previous work that dealt with 2 buyers. And we optimize over direct mechanisms. A direct mechanism is specified by an allocation rule X and a payment rule P, such that each bidder submits her valuation VI perfectly, truthfully, giving rise to a valuation vector V, such that each bidder I is allocated with probability XIV and pays PIV, which are functions of everyone's report. These mechanisms are subject to dominant strategy, incentive compatibility, and individual rationality constraints. These incentives constraints mean that everyone prefers to report her true value and to participate in the mechanism in the first place. And the dominant strategy part means that these incentive constraints hold for every valuation. So it doesn't require that bidders are Bayesian or know about other bidders in order for them to be truthful. This is a form of robustness against misspecification of agent behavior. Now we focus on the distribution classes, F. We want the mechanism to perform well against any distribution F in a given class, and so the objective is worst case over all such distributions. We assume that we know the upper bound of the support, which we can, without loss of generality, normalize it to 1. And we consider different dependency structures from arbitrary joint distributions to IID. This Venn diagram shows the distribution classes that we will consider. On the one end, we consider arbitrary joint distributions where the dependency can be general. On the other end is IID, where bidders are independent and identically distributed. We can further constrain the arbitrary joint distributions by requiring that agents are exchangeable. That means that agents are in some sense symmetric and can be permuted. It turns out that under these two distribution classes, the worst case distribution is that there is effectively only one active random bidder, so valuations are negatively dependent. But in practice, most valuations that we see are positively dependent, so we want to extend the IID class to capture these positive dependence. One such class is mixtures of IID. Another such class is exchangeable and affiliated. And we will discuss what these terms mean in the next slide. As we have already said, exchangeable means that agents are symmetric and can be permuted. Affiliation is a standard notion for positive dependence in classical or Bayesian auction theory and mechanism design. Roughly, affiliation means that a high value of one bidder's estimate makes that high values of the other's estimates more likely. And while affiliation is commonly studied in Bayesian settings, we are the first to study it in robust settings. Lastly, mixtures of IID are commonly used in statistics and modeling. One interpretation of this is that there is a hidden random type and agent valuations are IID conditional on that random type. We can also show that mixtures of IID implies that any two agents have non-negative correlation in valuation with each other, which further supports the idea that mixtures of IIDs captures positive dependence. We now focus on the objective. The objective is the regret on revenue, which is the difference between the benchmark revenue and the mechanism revenue. And here we focus on the regret because the gap between the IDU performance and the actual performance is an interpretable quantity. And here we take the benchmark to be the maximum possible achievable revenue when the valuation is known, which is the highest out of n valuations. We can also interpret this benchmark as a social welfare benchmark because this is the social welfare that is achieved under any efficient mechanism, that is a mechanism that always allocates to the highest bidder. We can now put all the ingredients of the problem formulation together and write the problem mathematically. So given a distribution class F, the seller moves first and chooses a dominant strategy incentive compatible mechanism. Nature then moves second, chooses the distribution F, such that the seller wants to minimize the regret, and nature wants to maximize the regret, where the regret is expectation over F of the difference between the benchmark revenue and mechanism revenue. This is robust in two ways. First, it is robust to distributional knowledge because we have guarantee over all F in a given class. The mechanism doesn't need to know F and is independent of F. Secondly, it is robust to models of agent behavior because of the dominant strategy. Our main contributions are summarized in this diagram. We prove that second price auction with random reserve is minimax optimal across many distribution classes F. For IID distributions, exchangeable and affiliated distributions, and mixtures of IID distributions, these three classes that capture positive dependence between agent valuations all have the same minimax optimal mechanism and performance, which depends on n, while the other two classes, exchangeable and all distributions that capture general dependence, they also have the same minimax optimal mechanism and performance, which reduces to the one bidder case. So the main theorem first states a structural result that under the three distribution classes that capture positive dependence, the minimax regret admits as an optimal mechanism a second price auction with random reserve with support from some R star to 1. We can also write the reserve CDF explicitly. We can also calculate the R star, which is the support, as well as the minimax regret value. This means that our result is not just an existence result. While we prove that the second price auction is minimax optimal, we can also characterize it explicitly, which means that we can make quantitative statements about the mechanism, as well as evaluate the value of competition, and so on. Our work is related to different strands of literature. There is a long line of work in classical mechanism design, pioneered by Meyerson, that we depart from it by relaxing the common prior assumption. The closest body of work to us is considering minimax regret on general distributions with bounded support by Birchman and Schlag, Aaron and Maclaras, Caldente et al., and Kokijit et al. Some other works consider IID bidders, but only with 1 or 2 bidders. Other works maximize revenue rather than minimax regret, such as the previous talk, as well as the later talks as well. Or consider other forms of robustness. There is also a significant work in the algorithmic game theory literature that prove approximation ratio results, but they tend to focus more on proving bounds in more complex settings, whereas we focus more on proving exact optimality results. There is no such exact optimality results before for an arbitrary number of buyers, IID, and affiliated, and this is the focus of our work. The challenges of our problem is that the space of all mechanisms is large, the space of all bounded distributions is large, and most importantly, the problem is non-convex due to class restrictions such as IID. We believe that the methodology that we came up with to tackle these is also of independent interest and is useful in other problems as well. Our approach is via a saddle point argument. So let RMF be the expected regret with mechanism M and value distribution F. The well-known saddle point theorem says that if the saddle inequalities hold, then M star is an optimal mechanism and F star a worst-case distribution. These conditions say that if you fix mechanism M star, then F star is optimal over all F, and if you fix F star, M star is optimal over all M. Intuitively, this is true because we can think of this as a zero-sum game between seller and nature, and this condition describes a Nash equilibrium where both players, seller and nature, are best responding. Seller chooses mechanism M to minimize regret, and nature chooses distribution F to maximize regret. We will then use necessary conditions to pin down M star and F star in a principled manner. And this diagram outlines how we do that. We first start with RMF, which is the regret with mechanism M and distribution F. We then make an educated guess that the optimal mechanism is an SPA with reserve phi. So we have R phi F here, which we can rewrite with integration by part in two ways. The first is regret phi, which is linear in phi. The second is regret F, which is a separable function of F. We first focus on regret phi. By the seller side of the saddle inequality, we know that phi star is optimal over all phi given optimal F star. By first order conditions, we then know that the coefficient of every phi term in the regret expression must be 0. This gives an ODE for F star, which pins down F star. Now we look on the nature side in regret F. F star is optimal over all F given phi star. Because the regret expression is a separable function, we can do pointwise optimization. And so by first order conditions again, we get an ODE involving phi star and F star. But we have already determined F star. So this gives an ODE for phi star, which allows us to determine phi star, the optimal reserve CDF. We can then look at the structure of the optimal mechanism. Previously, Bergman and Schlag, 2008, only solved the one bidder case. And our work significantly generalizes Bergman and Schlag, where we can characterize the minimax optimal reserve CDF for every n, as seen in this slide. So far, we have mostly mentioned NIID bidders, but we would like to emphasize that our results also apply to many distribution classes. In particular, like IID, exchangeable and affiliated, and mixtures of IID distributions. And to prove this result, in the exchangeable and affiliated case, we need another technical innovation where we prove novel bounds comparing order statistics of distributions in this class. We can also evaluate the value of competition, where for classes of distribution that capture positive dependence, the minimax regret value decreases in n and converges to a positive value as the number of bidders grows large. This means that competition has some effect, but there is also an unavoidable gap between the ID and the actual performance. Whereas for classes of distribution that capture general dependence, the regret is always 1 over E regardless of the number of bidders, so competition has no effect in this case. So far, we have solved the case of support 0,1 or 0B, where the upper bound B of the support is known. We can also characterize the minimax optimal mechanisms in the case when both the lower bound A and the upper bound B of the support is known in the same framework with n buyers and all the 5 distribution classes that we mentioned before. Where for A over B low enough, the same SPA is still optimal. For A over B high enough, another variant of SPA is optimal, where instead of discarding the item with some probability, that is, in the SPA, when you are below reserve, we instead allocate the item to everyone else but the highest bidder. And for A over B in the intermediate regime, some form of interpolation between these two mechanisms is optimal. Apart from the regret objective, we can also calculate the maximum approximation ratio objective, where the ratio is defined as the ratio between the mechanism revenue and the benchmark revenue, where we can transform the ratio objective to the regret objective via an epigraph formulation. To conclude, We undertook a systematic study of prior independent mechanism design, where we give closed form characterization of a minimax optimal mechanism, knowing only the upper and lower bounds of the support. And we accomplish this in a general framework with n agents and several distribution classes, IID, mixtures of IID, exchangeable and affiliated, exchangeable, and all distributions. Our results show the strength or lack thereof of different distributional class assumptions and quantify the value of competition. There are many avenues for future work. We can look at different support assumptions, different benchmark, different notions of robustness, and we can ask further questions about what the value of additional information about the distribution would be. That's all. Thanks for listening, and I welcome questions.
Let's start in the room again.
Yeah, related to this question.
Hello? Oh, hi, sorry.
Yeah, related to this question about additional information. So, do you have any idea about what test statistics or what like a small number of samples might do to give you a much stronger, like maybe you can do something much better with like some small amount of information about the distribution?
Yeah, we are very interested in that. I don't think we have like results right now in that direction.
Do you think it would be possible to use a similar approach for selling more than one item?
We believe that it is possible. We know that it is possible in the case of arbitrary distributions and exchangeable distributions, the general dependence classes that are in some sense easier. We haven't worked that out for like IID and positive dependence distributions, but we believe that they should work.
Yeah,
Thanks.
So you have, I guess, 3 classes of positive correlated distribution. All of them have the same optimal second price optimist reserve. So I guess whether like, is it possible that for all positively correlated distribution, they have the same solution?
It is possible. We have to define what we mean by positive dependence. And like these are like 2 notions that we define, and we use them fairly heavily in our proof. But it is quite possible and very interesting prospect. Thanks for the question.
In your open questions slide, you mentioned you could consider other benchmarks.
Mm-hmm.
What would those be, for example?
So another benchmark that we are thinking about is the opt benchmark, where we know the distribution F, but you do not know the valuation. So the optimal would be the Myosin or the Aryan valuation thereof. So because this benchmark assumes that you know the valuation, so this is like when you know a bit less.
Questions on the chat?
Are there questions online?
Yes, there are actually 2 questions. Namely,
Hi. Oh,
the first
yeah, I
one.
think this is a related question.
So can you read those? Maybe can you just react to them? So I don't have to read them out loud.
Yep. So I think there are 2 questions. First is that why regret? So one is that regret is an interpretable quantity, is a gap between ideal and actual. The other way to motivate regret is that it's a way to give scale to the problem, because if we max min the revenue directly without constraint, the worst case would just be 0. One way to do it would be to add additional constraints on F, say that you know the mean constraint like the previous talk, whereas like here, like in some sense the scale is endogenous because we put the max there. And another question is that why this benchmark? We agree that there are many interesting benchmarks. One is that suppose that we can prove the if we can prove the upper bound on the max benchmark, then the weaker benchmarks would also follow as well in terms of upper bound. Another is tractability. Our method works better with max benchmark. We believe that with some work, they can probably be made to work with opt benchmark as well, and this is what we are actively working on. Thanks.